Hi everybody, today I'm visiting the University of Oxford and I'm here to talk to Professor Tim Palmer about climate models. Tim, on the weekend I read this article in the New York Times that was titled "How Scientists Got Climate Change So Wrong." And it was mostly about weather extremes and said that climate change has been much more abrupt than climate scientists expected. And I was wondering if that's really the whole story, because I kind of remember that people were talking about tipping points and unstable equilibria already in the 80s. So I was a little bit surprised about this, and I thought maybe I should ask you what you think about this.
Well, the first thing to say is it's kind of interesting that now, for decades, having been attacked by the climate skeptic stroke denier community that the models are somehow useless, now the attack is coming from the other side, saying the models are somehow too conservative and not telling us enough about the extremes. Now, I guess there's a couple of points to make here. The first thing is, from a scientific point of view, most of the focus of the model predictions has been of global mean temperature. And the reason for that is sort of, because that's the basic thing that increased carbon dioxide is doing to the atmosphere. It's increasing the surface temperature. And by measuring the global average of this, what you're actually doing is measuring or predicting a quantity where the signal to noise is maximal. The signal being the effect of the carbon dioxide forcing that we're putting into the atmosphere, and the noise being the internal variability of climate, the fluctuations that really have nothing to do with increasing levels of CO2, but just arise from the natural chaotic variability of the atmosphere. So when we go onto global scales, the chaotic variability is actually at a minimum, and the impact of the CO2 forcing is at a maximum. So from a science point of view, that actually is a very kind of robust indicator of how carbon dioxide is changing the climate. It's warming the global temperature. And actually, I would say that the models from the 20th century through to the present day have been remarkably accurate in predicting the rise in global temperature. So from that point of view, I don't think the models have been, underestimating the effect of carbon dioxide on global warming. However, when we come to talk about more regional extremes, so things like particular heat waves, could be over Europe or United States, or flooding events, or intense hurricanes or tropical cyclones, or indeed, as you say, kind of tipping point types of phenomena, then you're dealing with a situation where the internal variability of the atmosphere is much greater, and the signal, therefore, relatively speaking, is smaller. So it becomes a more difficult statistical exercise. But on the other hand, this is exactly what people want to know. I mean, nobody physically is affected by global mean temperature, but they are affected by extremes of weather. And I think basically what the article is correctly pointing to is the need, now we've established beyond doubt, I would say, that humankind is warming the planet. We need to think in much more detail and much more accuracy what this implies for regional extremes of weather and climate. So there are two issues here. One is developing the sort of statistical techniques where we can be confident in saying that such and such a weather event or a climatic event had an anthropogenic component. In other words, part of it was due to the fact that we're increasing CO2 levels. But it also puts very much an onus on climate models to be able to simulate these extremes well. And actually that's an area where I think we can still improve things considerably. So I think that the article, I think it sort of exaggerated some aspects of the issue, particularly in relation to global mean temperature. But it correctly drew attention to the fact that we do need to focus much more on our ability to simulate and predict and assess how extremes of weather and climate are being affected by climate change forcing.
So speaking about the quality of the predictions, you told me something about this figure 9.8 in the IPCC report. And this took me forever to understand, but I will try to summarize what's in the figure, and then you tell me if that's about correct. So what you see in the figure is the temperature anomaly for a period of years. And so the temperature anomaly is the global temperature, basically, up to a reference value. And this reference value on this figure is in the yellow region, which is from the years 61 to 1990. And so all the thin squiggly lines are the predictions from the different models. And the red line is the average from the models. And the three black lines are the data from different organizations. And so what I didn't understand forever.
Well, just to correct you, it's not the data from different organizations; it's how different organizations analyze the data to, the common data sets to produce estimates of global temperature.
Yeah. So what I didn't understand forever was what's this little bar on the right side where it says mean temperature. So that's the actual temperature, the absolute temperature that these models predict in this region from 61 to 1990. So basically it tells you that the spread in the absolute temperatures is much larger than the uncertainty, the little squiggles in these models in the whole region where they have data, right? So I think what this figure tells us is that the models all agree that there is a certain trend, looks pretty good, in terms of forecasting. But it also tells me that, the models have some difficulty getting the absolute temperatures right.
Yeah, it just highlights the fact. I think perhaps it might be worth backing off a bit here and saying that these models are attempts to represent the climate of the Earth from pretty much first principles, from the basic laws of physics. So from Newton's laws of motion, as expressed in, what are called the Navier-Stokes equations of fluid mechanics, to equations which basically represent the laws of thermodynamics in a sort of in terms of differential equations, coupled together with laws which express more quantum mechanical laws, which express how photons from the sun are absorbed by different molecules and so on in the atmosphere, and re-radiated back to space in the infrared. So these are all very basic sort of equations. They're not, it's not that we're just kind of guessing empirically how we think the world works, by just sort of drawing equations out of a hat and putting them into a computer. These are the basic laws of physics. Now, if you look at it from that point of view, trying to get exactly the right, to simulate exactly the right surface temperature of the Earth, which you have to remember, over the oceans, the surface temperature is a very sort of complicated balance between, regions of where the ocean is, ocean water is sinking, and other areas where it's rising to the surface, and regions where the sun warms the surface, other regions where you're under cloud and there's very little sun. So getting the surface temperature not only requires, for example, getting the dynamics of the ocean right, it requires getting all that cloud cover right in the right place. So it's a really, really, really complicated and difficult thing to get right. That's the first thing to say. And the little bar on the right-hand side is just pointing out that actually, it's a kind of manifestation of that problem, because the range of estimates of global mean temperature from the models actually range over a few degrees, which is much larger than this trend in temperature that we've seen over the last 60, 70 years or so. Now, I don't think this particularly undermines, well, it doesn't undermine the projections of global temperature. I don't think it casts any doubt that the trends in temperature that we've seen over the last 70 years are indeed directly associated with human emission of carbon dioxide. But what it indicates is that, we still have some way to go before we can say we have simulated the climate system to the extent that you really can't tell now. If I show you output from a climate model, you can't tell whether you're looking at a model or the real world. We still have some way to go to do that. And that's becomes particularly important more at the regional level. For example, we talked a little bit earlier about tipping points, and these are kind of what you might call very non-linear transitions, sudden transitions in the climate system. Getting these right actually does depend on getting the actual absolute values of temperature right. So, for example, if you take the melting of, there's a concern that the melting of Greenland ice, and actually the sort of disintegration of the Greenland ice core caused by, the lubrication of the surface, the bedrock from melting water. That requires models to get the temperature right, because fresh water at least freezes at 0 degrees. So if you have a 2-degree bias or something, that you're going to get that process wrong. Another example is possible tipping points for the biosphere, where either due to heat or a combination of heat and availability of moisture, of rainfall, a forest can suddenly become no longer self-sustaining and will collapse. But again, to be able to model that requires getting these temperatures and rainfall amounts not right in a kind of anomalous sense, but getting right absolutely. And all that, I think that what that bar on the right-hand side, I don't think it should make us doubt at all that the temperature is warming due to CO2. But what it's indicative of is the fact that we, particularly now as climate really starts to become an important societal issue, we've got to step up a gear in getting our models bias-free.
Yeah, so this bar on the right side, this was one of the things that I didn't really understand about this figure. The other thing is that I find it peculiar that you have the prediction from these models, but the predictions don't have any uncertainty attached to them, which is what I would expect would be the output of such a model. So my understanding is that the figure that for the projection of the increase in temperature until the year 2100 or something in the IPCC report, it has an uncertainty, and that's basically the spread in the predictions from the different models, not actually the uncertainty from the models.
Okay, so the first thing to say is that the whole philosophy underlying the IPCC report is that it's an assessment of the state of the art of climate science as determined by the peer-reviewed publications that exist at the time the report is written. Now, there are many climate institutes around the world. Typically, certainly virtually all of the bigger countries of the world have their own weather or climate institutes. And they have their own climate models. They might be literally their own model produced by scientists in-house, or they might have taken the code from another institution and maybe done some modifications. and produced results with that model. Now, many institutes do not have sufficient computing resources to actually run the model itself in a kind of ensemble mode, where they might produce 50 projections, where you try to by a number of different possible ways of representing uncertainty in particularly the so-called subgrid parameterization. So that's the most uncertain part of climate models. You have to represent processes, cloud processes, perhaps the most important, which are occurring on scales where the model can't resolve. The grid spacing between the grid points in the model is larger than the typical size of a cloud. I mean, many climate models have grid spacings of many tens, maybe up to 100 kilometers, whereas individual clouds are just a few kilometers for the big ones at least.
So that's 100 kilometers in the horizontal.
In the horizontal, yes. It would be less in the vertical. So many climate institutes don't have the computational resources to try to explore the uncertainty in the subgrid parameterizations. So they would typically just have one run, or one or two, let's say. Other institutes may have multiple ensemble integrations where they do. I mean, the Met Office, the UK Met Office, is a good example, where they produce very large ensembles of climate change integrations, where they try to exactly do what you say, try to perturb the uncertain parts of the models, maybe using some kind of stochastic process, and then run these. But for these IPCC assessments, to avoid being dominated by, if one institute had 100 runs and the others only had one, you'd be dominated by the centre which had 100. So I suppose a way of dealing with that is just to make the assumption that the ensemble of all of these different models is itself a reasonable representation of model uncertainty. Now, you can argue whether that's true or not, and I would argue certainly again, coming down to the regional scale, that's probably not a good assumption. But I think for these global mean temperatures, it's not a bad assumption.
So what do you think are the main reasons that the predictions from the different models diverge? Well,
there'll be a little bit of divergence from chaos, if you like, that, if you just started them from infinitesimally different initial starting conditions, the butterfly effect will actually produce a certain amount of spread. But that's probably that isn't really the major contribution to uncertainty. It comes from the uncertainty in how to represent processes which are important for climate, but where you don't have the computational resources to resolve them. So you have to parameterize, to use the jargon, parameterize these subgrid processes with very simple, relatively simple anyway, formulae, which and then so you have a closure formula. So there is a basic assumption somewhere where you would say, okay, if I know the temperature in a grid box and I know the humidity in the grid box and maybe some other variables, the wind and so on, I can predict in a bulk sense what the amount of cloud in that grid box, whether it'll be completely cloud free or completely cloud covered, or 50-50 or something like that, half covered and half clear. So there'd be a formula which would be based on these resolved scale variables. Now, in reality, there isn't such a formula. It's not like nature. You can't go up and read a textbook on physics and discover what that formula is, because there is no formula like that. So different groups may come up with different formulae, different closure schemes. for various reasons. They may have some data sets which other groups don't have, which maybe supports their formula or whatever it is. I mean, my own view is that the only way to deal with this objectively is to express all of these subclosure schemes in a stochastic way, using kind of some ideas of random variables, and just acknowledge that actually, from a basic physics point of view, that is the best way to represent uncertain processes. But in any case, the origin of the uncertainty is this subgrid, the subgrid parameterizations, and of all of them, the most important are cloud processes. But there's also other things to do with how you represent topography, the mountains of the Earth. If you have a very sharp flow that's blocking, if you have a very sharp barrier that's blocking some flow, the width of the barrier might actually be too small to represent with your grid, with your finite grid. So you have to try to represent that blocking effect in a more approximate way. I mean, that's just one example. But and the oceans, the oceans have what are called mesoscale eddies, which are really important for determining how strong currents like the Gulf Stream or the Kuroshio current in the Pacific are. But again, modern day climate models, the ocean part of these climate models is the resolution is. I mean, we're starting to getting close to being able to resolve these types of ocean eddies, but we're not really there yet. So they have to be parameterized, and again, that's a source of uncertainty.
So I guess this brings up the obvious question: what can be done about it?
Well, you see, the issue. The interesting thing from my point of view is that climate has sort of gone in the last few years from something that, I mean, it's always been potentially of societal concern, but I think a lot of scientists felt that although the societal concerns were important, in a way that the tools that they had were, if you like, primarily being used for scientific research to really understand, the way in which, for example, enhanced CO2 emissions would impact on different parts of the climate system. It was a it's a scientific endeavor. But what's literally happened, in the last year or two, is that it's suddenly become this incredibly pressing societal issue. We're seeing all around the world these quite devastating weather events, which are, affecting people's lives, and society has got to know what can they expect in the future, and how can they better prepare for the future. What sorts of buildings do we need to withstand these extremes? Where should we be living to withstand these extremes? Can the human body actually literally exist in parts of the world where temperatures and humidities become, once they reach a certain level? So it's kind of gone from a societally important but fundamentally scientific question to one that really is societally crucial. And I think, therefore, as a result of that, we've got to think in a much more pressing way about making these models fully realistic and accurate, and really trying to eliminate, where possible, these parameterizations, which just are too approximate. And we know, in a way, the bottom line is the resolution of the model. In other words, the spacing between the grid points. That's what, that's having these grid spacings of many tens or hundreds of kilometers means that many of these important processes, key types of cloud processes, ocean mesoscale eddies, the flow over, orography, topography, whatever you we call it, have to be parameterized. We know if we can get the grid down to, say, about 1 kilometer globally, then we can eliminate, not all parameterizations, but probably the most important ones. And I feel, given this new sort of urgency to try to be able to answer questions which governments around the world and individuals around the world are asking about, and the New York Times article drew attention to, about extremes. How, I mean, this week, for example, in the UK, there was considerable flooding in an area near Doncaster. Hundreds of people had to leave their houses. I mean, that's the kind of key question a government wants to know. How much more frequent will that type of situation occur in the future? The poor people that suffered in Mozambique under these enormously powerful tropical cyclones, again, want to know how much more frequent are these unbelievably intense tropical cyclones going to be. So we've got to develop models where these biases and so on, are eliminated. And we can do that in principle, but like all scientific big projects, it requires a certain amount of investment, and it's primarily investment in supercomputing. It's to do with supercomputing.
So, I would certainly agree with it that this is information that we need. So I find it a little bit ironic that I keep hearing that the science is basically done. So I have another quote which I found in The Guardian in an article that appeared last week. It says, "For ordinary citizens, it is important to recognize that scientists have done their job. It is up to us to force our leaders to act upon what we know."
Okay, I mean, that particular quote was, I think, referring to the issue of trying to cut our emissions of carbon dioxide. I would agree, I think, more or less with that quote if all that we were talking about was, do we have enough evidence to make a decision about cutting our carbon emissions? Because in a way, it's like every decision you make in life, you don't necessarily have to know exactly what's going to happen to make that decision. You have to know the threat that you're facing and whether the decision is justified given that threat. Now, the one thing that climate models have been quite unequivocal about is actually that as if we continue to emit CO2 as we are doing now and as we have done, then by 2100, although we can say that the most likely amount of global warming might be maybe 3 or 4 degrees, we know from these ensembles of integrations that there is a tail which goes out to more than that. It could go out to 6 or 7 or even more than that degrees. Now, again, 6 or 7, I don't know whether that sounds a lot, but for anyone who knows their climatology, that really is catastrophic. So, I mean, I, as a scientist, I don't want to say that, that means that we must cut our emissions immediately, because that's a political statement. But I think the politicians, in principle, have enough information to make that decision. So the fact there is this threat, this risk, not only of very undesirable levels of climate change, but actually catastrophic levels of climate change, the risk is quite clear, and the only way to reduce that risk is to reduce our emissions. So from that point of view, I agree with the statement. But to say that the science is kind of all done and dusted, and the scientists are not needed anymore, misses the other aspect of the problem, which is that even if we cut our emissions to zero tomorrow, we've already put into the climate system a certain amount of climate change that will continue. Now, we're not going to cut our emissions tomorrow. We're going to carry on for sure for many decades to come. And so we are faced with a changing climate, and we are faced with decisions on how to make society more resilient to that changing climate. And I think nowhere is that more important than in the developing world, who, after all, have had absolutely nothing to do with this problem. I mean, they have not caused it in the most minute way. But in a way, they're likely to suffer the most, either from extreme levels of drought to these really occasional but exceptionally damaging storms, or to levels of, as I was saying to you earlier, to periods where temperatures and humidities could get so high collectively that the human body can no longer lose heat, either by sweating or any other means. So, then that becomes an existential threat. So that's sort of what we've got to do better, I think, in quantifying, and that puts very much the onus of climate change at the regional level, not just on the global mean temperature. My own view is that this is a little bit like, the famous Marshall Plan for bailing out Europe after the Second World War, where the US pumped large amounts of money into stimulating the European climate, the European economy, not particularly for an altruistic reason, but because they feared the spread of communism and they wanted to stop that. Now, you could very much view that the whole investment in climate adaptation in the developing world could similarly be viewed at a very, self-interested level, in the sense that we're already seeing, migration, in Europe from Africa and the Middle East, in the United States from Central America and South America. And there are certainly aspects of climate change in the reasons why people are migrating. Now, this is potentially nothing compared to what it could be like, in later in this century. And so I think a kind of modern day Marshall Plan by the developed world to try to make life just more bearable in developing world would like the Marshall Plan to stop communism, this would be to try to keep people in place and say, actually, living where you are is not so bad. But if it becomes unbearable, then the trickle of migration that we're seeing now will become a torrent. And so that's where, again, I think the climate science is not done and dusted, because we don't yet have a good and, I would say, reliable picture of how these extremes of climate at the regional level are changing, and whether, for example, these tipping points, as they're called colloquially, but these kind of sudden, rapid changes in climate which cannot be reversed. I mean, that's the key point about a tipping point. You can't reverse it. Once it's flipped into this new state, it's irreversible. This, by the way, has this is actually where this actually has a kind of a feedback into this question of emissions reduction, because there's certainly a body of political thought which says, well, cutting our carbon emissions today is really, really difficult for various political reasons. But we don't have to worry, because in 50 years' time, we'll have developed the technology which will enable us to suck the CO2 out. We'll suck it out of the atmosphere and dump it underground. And so we don't have to be too kind of aggressive in our emissions cuts today, because that will be a technology that will be there in the future which will help us. Now, the point about that is, if in that period before the technology has been developed, if it ever can be developed, which is a major question mark, I would say, if we have undergone these tipping points, for example, in Greenland ice or some of the biosphere, or indeed some ocean dynamics might potentially have that capability, then you've gone to a state that you can't reverse. So sucking the CO2 out of the air once the tipping point's happened won't do any good at all. You're not going to recover back to where you were. So again, that's an area actually where I'm slightly contradicting myself, because I was saying that we perhaps need we have as much knowledge as we need to put into place emissions cuts. But I think the question about whether we can delay emissions in the hope that sort of the sucking it out of the air at some future stage will occur. That's going to be totally ineffective if we actually have crossed some of these tipping point things. And that requires knowledge of the climate system at that much more regional level, and also at a much more detailed level, because tipping points inevitably involve quite non-linear processes which are hard to simulate accurately, and that's where you need good models.
I think that's a good place to stop. Thank you for your time.
Oh.
Thanks everybody for watching. See you again next week.